Welcome to our third video of this tutorial. So far we have seen that the standard scalar is the best fit for our existing dataset, and we have assessed the model based on support vector machine, which can explain more than 86% of the variance of the training dataset and around the same percentage of the variance for the test dataset. And the prediction accuracy we found that is plus minus 2.3 depending on the mean squared error, which we saw around 5.5 for the training and testing dataset. So if we want to improve the performance of the model further, let's check different kernels for the model, and for this we use the same lines of code as we used earlier. For example, we see in the beginning we split the dataset into training and testing set, 80% and 20%. With the help of this library, train test split. X1 is the weather data, energy is the energy data, and then we flatten the arrays for the training data and the testing data, and then we build the regressor, that is the regressor model with the polynomial kernel. And here we define the degree for this polynomial kernel, which actually looks like this equation to predict the value of y. And then we train the model like with the fit command, and based on the trained model we predict the energy values, and at last we test the model training accuracy with the help of R squared score and mean squared error. And we see the performance really bad, and the error is more than 15. So that means if we predict 100 kilowatt hour consumption of the building, it will vary around a root mean squared value of 15, and that is a lot. So let's see if we can improve the performance in different way. For example, we have removed some of the weather parameters earlier. See if we add them, then let's see if they can improve the performance of the model. When we add all of them, but one thing to remember that relative humidity and the hourly sum of precipitation, they had the same correlation if we check the heat map of the correlation, so that we can select either of these two weather factor. So let's remove the relative humidity and put a new variable name, that is x4, and we scale the weather file knmi, and with this curly sign again we just remove this data of the relative humidity. So the complete weather data we have then using here when we split with the weather file, weather data and the energy data, and then 80% for training and testing for 20%, and then we follow the same steps, and we again go with the default parameters for RBF, that is radial basis function kernel, and then when we train we predict, and then we see the performance is slightly higher than the previous one. So we can we can actually go with the previous weather file just to avoid further complexity of the dataset. But for the sake of this tutorial, let's continue with a slightly improved performance of the model. So how it actually looks when we check the test dataset as well, we see this is very similar. That means they are not overfitting or underfitting. And if we want to see visually how the original data and the predicted data looks like, then let's plot it. With this line we are defining the figure, and with figure size we will see the width and the height of the figure, and then with plot we put the data, and when we put only one data set, that means the index will be on the x-axis and the value will be in the y-axis, and then we put label. Then again we plot prediction, so index will be in the x-axis and the value will be in the y-axis, and then we label the data. And when we define the location of the legend, the best actually brings by the model where it actually fit the best. Like these labels will be visible here in the right corner, and then we put the x label and y label. So this is how we see that it is actually missing the edges, because it's within this variance based on the r squared score. We see that around 86% is within the range that the model can predict. Well, so now we can improve further just to improve the hyperparameters, because so far we have considered the default values, which was 1.1 and scale for the gamma value, and there is a method to define the value for gamma, and we then check the we can check how we can improve the performance. For this we can use the grid search library. What it does, that if we import the library from sklearn, then we can set some parameters. Like we check parameters, we define some values for C, and then we define some values for epsilon, and then we define some values for gamma, and then we put these values according to the model that we have found within this grid search cross validation function. And what it does, that when we define in jobs equals to -1, that means the model will continue running until it gets the best parameter for us, which actually gives the highest prediction. And then cross validation, we by defining 3, it actually shuffle the data frame into 3 parts, and each iteration it changes the individual section of the data set as a training set and the test set. So there are a lot of calculation behind this and so many iteration, and when we train the model based on this training data, it will give us the best parameter based on this function. And the whole code, it will take more than an hour to complete, and then we find the best parameters as these, like the 30.03 and 5. One thing to note is it is in the highest edge and this is in the lowest edge. That means our parameter selection can be further optimized if you want to improve the performance. So let's check how the performance improved, just by defining the model with this kernel and specified parameters. We see is really a little bit improvement, so not much that we expected. And again, if I improve the value for C from 30 to 40, again the value does not change. So far this is what may be the best that supervector machine can offer us. Let's now check what random forest regression model can provide us. For this let's wait for the next video where we will go through the details of this model. Till then, have a nice day. Bye.